All right, geometry video 2 for lesson 12.4. Here we go. So a binomial experiment, right? So a binomial experiment, and this prefix bi means two. So for a binomial experiment, it consists of a fixed number of trials, okay? So a fixed number of trials. Typically, we let that number be n, okay? Where each trial has two possible outcomes, okay? Success and then failure. The results are independent, right? So it should be with replacement, all that fun stuff. And then the probability must remain the same. So this has to be a consistent probability. It cannot change. That's kind of linked with independence, right? So that probability has to remain the same. Now, when I taught statistics, there was an acronym called BINS for this, B-I-N-S, right? So BINS means binary. So binary stands for two outcomes. And again, it's success and failure. Success, failure. Then I for independent, right? So make sure, so binary, independent. Okay? Next, N for number. So number of trials fixed. So the number of trials is fixed. And again, typically this is your N value. And then S stands for success. Probability is the same. So success probability is the same. And that typically is your p-value. So there we go, right? So when you come across a situation, first thing is you ask yourself, is it binomial? And then you go ahead and attack it. All right, so let's take a look at a couple examples involving a binomial and binomial distributions. Okay. All right. Example 3 here says, is the experiment a binomial experiment, right? So it says the spinner is spun 3 times. Assume that the spinner is equally likely to stop in any of the sections. Your success is landing on a section marked go forward 2 spaces. Okay. So let's take a look here, right? So we need to do our 4 letters, B, I, N, S. So B. First off, are there 2 outcomes only? Okay, well, what is our success? So in this case, a success is going forward 2 spaces. Go forward 2 spaces. So I know that there are a lot of different opportunities, right? This is your, so we have what? Go forward 2 spaces here. We have a go forward 2 spaces here, right? So those are our 2 spots, here and here, right? So then there's 1, 2, 3, 4, 5, 6 other spots, but we can just let failure be not getting a go forward, not go forward 2 spaces. And that ensures that we have 2 outcomes, what we want and what we don't want, right? So we don't focus on all the different not outcomes, we just lump them all together, okay? Next, so we passed that. Next, I for independent, right? Notice here that it doesn't matter what the first spin was. When we spin the second one, it's going to be independent. There's no replacement, not with a, so this is going to be independent. So each spin, so again, when you're deciding about independence, you kind of have to either know the situation or the words tell you it is or it is not. So each spin is going to be independent. So we're good there. Okay, N is the number of trials fixed. So yes, you're going to spin the spinner 3 times. So the number of spins, N, equals 3. So we're good there, okay? And last but not least, the same probability. Is the probability the same for your success? Well, remember that your success, so P of your success is going to be the probability of getting a go forward 2 spaces, right? Go forward 2 spaces, this is your success. So we have 1, 2 of those spaces out of a total of 8 total spaces. That's a 1 out of 4 chance. And that probability never changes for any turns, right? That's the same probability for each turn. So this would be a binomial situation. So yes, it's binomial. Great. Okay. All right, very good. Let's do another problem involving whether it's binomial or not. And if that was binomial, let's guess what this one's going to be. Okay, so in a class of 23 students, 7 students completed the term project. 2 students selected at random have to give presentations. Success is that the student has completed the project, right? So we're going to take a look at, is this a binomial experiment? Well, let's take a look at the 4 letters. First, Ben. 2 outcomes. Are there 2 outcomes? Well, what would be a success here? For us, a success would be that the student completed the project. So success equals completed. So then failure is not completed. Next is the independent. So it is binary. Next is the independent. And let's take a look at that using a tree diagram. Okay, so we're selecting 2 students. So here's my starting spot. Right, here's my 2 students. So either they they completed the project, or they failed. And this is the first student. So if you look here, 7 students completed the project. So our probability of a success is 7 out of 23. Remember that these 2 branches have to add up to 1. So then if 7 completed it, then 16 did not, right? 23 minus 7 is 16. Okay? And now, after we pick the first student, we have to pick a second student. And here's where the problem lies, right? When we pick this second student again, they could be a success or a failure, a success or a failure. But when you pick the second student, you can't pick the same student twice. So after your first selection, if you picked a student who did successfully complete the project, then you only have a 6 out of 22 chance to pick another student who successfully completed the project, right? And if I just continue filling it in, here, if the first one completed it, then you have a 16 out of 22 chance that someone failed it. Again, have to add up to 1. Down here, if the first person failed, then you have a 7 out of 22 that the second person succeeded. And here, if the first person failed, then you have a 15 out of 22 chance that the second person also failed or did not complete. And again, they add up to 1. But you notice here that the probabilities are changing. Notice that this bottom number went from 23 to 22. The probability of success on the first student is not the same as the probability of success on the second student. So because they are not independent, the probabilities are changing, right? So this is not independent because the probability changes. You can't pick the same student twice. So not independent because of that situation. So it's not independent, therefore it's not binomial. So this would violate the independence and also the probability being the same. All right, very good. Okay, so now that is talking whether it's a binomial or not. So now what if it's a binomial? What can we do going forward? Okay, well, here is our formula to find a probability based off of a binomial experiment. If we have n trials with a probability of success p, so the probability of success p, and we want to pick exactly our successes, all right, then here's our formulas, right? This is the layman's terms. So this is the probability of getting our successes is the number of ways to get our successes. And again, order doesn't matter, so that's why we use combinations here, right? No order. We just want to get the total. And then we take the probability of getting that many successes. So you take the probability of a success raised to the r power. And what that means is, and I'll do it right here, that is, so the probability of success times the probability of success r times, right? And that's just your standard exponent rules, right? And then here, the 1 minus p is the probability of a failure times the number of n minus r failures, or how many failures there are left. So again, this is then failure times failure. How many times are left, right? N minus r times, because you have to have, right, a total of n events, right? 1, 2, 3, 4. This so all of these together must add up to n. This is your r times. This is your n minus r times. And this is the formula you have to remember right here. And again, not have to really remember. I'll give it to you on a test or something. But this is your probability, your binomial probability formula. And we'll take a look here. And again, I'll expand it out and then we'll do it using the formula. All right, so this is our last example for this video. So it says, a grocery store gives away scratch-off cards with a purchase of more than $100. Terrell has 5 scratch-off cards. What is the probability that he has exactly 3 winning cards if each card has a 30% chance of being exactly a winner, right? So this is binomial. We're not going to go ahead and do this. So to do this problem, we need to understand what we're looking at here. So we have 5 total scratch-off cards. We want 3 winners. So in this problem, our n value is going to be 5, right? And our r value is going to be 3. And each card has a 30% chance of being a winner, so that is our probability of being a success. That's our p-value, 0.3 or 0.30. Okay, so now let's work this out, okay? So let's recall from our 12.3 lesson that we can find the number of combinations. So let's do this. Number of combos. And again, let's assume our 5 cards are A, B, C, D, E. So we want to pick 3 winning cards. Okay, so how many outcomes are there? Well, there's a total of, let's see, so A, B, C, and then A, B, D, and then A, B, E. So that'd be those combinations with A first, right? And then we could do A, C, D, A, C, E. And then we could do A, D, E, right? So that'd be all the A's, okay? Now let's go B first. Now we're not going to do BAC because that's the same thing, right? So BCD, BCE, and then we'll do BDE, and that's all the B's. And then we'll do CDE, and that's all the C's, right? So it's 3, 6, 9. That's a total of 10 times, right? 10 different outcomes, okay? Okay, so that's the number of ways you can pick 3 cards out of 5, right? And remember, that's just going to be our NCR, right? So we have 10, choose 3, and that's going to be in our formula, right? Okay, so now we want 3 winning cards. So to find the probability of getting exactly 3 winners, we're going to take the 10, because there's 10 ways to pick 3, and we want 3 of them to be winners. So the first 3 spots are going to be success probabilities. So 0.3 times 0.3 times 0.3. Those are successes, right? So this is our 3 successes. And then the next 2 spots must be our failure probabilities. So this is going to be 1 minus 0.3. So 1 minus 0.3. And then 1 minus 0.3, right? And this is our 2 failures. And that's how we get that binomial formula with the 5 spots total, because we're choosing from 5 cards, right? So it should not have been over here. I apologize. This should not be 10, choose 3, right? Your n is 5. I have it right up here. 5, choose 3. Okay? So then if you multiply all this out in your calculator, again, these are 0.7s, so I would change those to 0.7s. If you do that in your calculator, you're going to get 0.1323, 0.1323, which is 13.23%. So whatever they want, right? What is the probability? Either of those are good. Now again, if you just use the formula, and again, I would give this formula to you, so the probability of getting 3 successes would be 5, choose 3, so how many different ways to pick 3 cards, times the probability of a success, 0.3 raised to the 3rd power, times the probability of a failure, 1 minus 0.3 raised to the n minus r power, 3 minus 5 power. So again, this is 0.7, the exponent is 2, and that's where you get these 2.7s. And again, if you did the same thing, you would still get that percentage. Okay. Remember your 5 choose 3 formula. So again, 5 choose 3 is going to be 5 factorial over 3 factorial, 5 minus 3 factorial. So that's 2 factorial. So again, if I expand this, I'm going to do it up here. So 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And 2 factorial is 2 times 1. So the 3, the 2, and the 1 cancel. So this is 20 divided by 2, which is 10, which matches that right there. Okay. So again, You don't have to do all of this. This is not what you need to do. This is all you need to do. Use the formula and get the right answer, right? But this is explaining where the formula comes from. All right, very good. All right, so best of luck on these probability and binomial distribution problems.